Okay, our fourth section in this chapter really is dealing with radian measure and arc length. So you can see our learning goals today. We're going to be able to convert from degree measure to radian measure and back and forth, and also how to find arc length. Now, knowing that, let's get started and try this. When we talk about radian measure, you have to realize that the radian, and as we've sort of been describing this week, as some of you know that exists, the radian is a measure created so that the arc measure and the arc length use the same number. So when they were going about it and saying someone was measuring the arc on the circle, and and so we wanted to know, here's our center and there's our radius, and so we wanted to know what is that arc length, which is that part here. And so that came in one measurement, and then the degrees of the angle were different. And so someone said they wanted to do it so that it would be equivalent. So the radian is a measure of an angle, arc, or rotation such that pi radians is equivalent to 180 degrees. Now, some of you right away will say, well, wait a minute. Pi radians, that's not a real nice number. So if you say 3.14-ish, and actually, as you know, you can use your exact value decimal approximation on your calculator. And if we would do that division, and I didn't do division, we would find out that if we wanted to solve for 1 pi, so really all I did here to get my 1 pi was divide both sides by pi. So I end up with 1 radian now, when the pi's cancel. 1 radian is equivalent to 180 degrees divided by pi. And if you notice, that's approximately 57.295, etc., degrees. So a radian is almost 60, but not quite, right? And that's it. That's the measurement they came up with compasses and protractors, radius, everything that they had when they worked through things. Now, question will be, we got to be able to know both systems. So take a good look. What we just talked about is exactly what the conversion factor is going to be. It just depends on what do you start with. So looking at if we have radians and we want to turn it into degrees, we will multiply by 180 degrees divided by pi radians. So 180 degrees divided by pi radians, that would give us the radians would cancel. That's exactly what we want, and only leaves degrees. So if you think about it, what remains in your answer, or what you want to remain in your answer, is what the top value is. So down here when we've got degrees and we want to change it to radians, start thinking, hey, I want radians remaining. That's what your multiplier. Otherwise, the fraction is nothing more than the inverse reciprocal flip of each other. So whatever you want to have remaining in this final answer is what you should have as your multiplier up top in the numerator. The other piece goes in the denominator. So knowing that, and again, some of these will be with a calculator, some of them will not. If we say convert each degree to radians, so right away you're saying radians, well then that means we need, this should be a multiplier, pi on top and 180 degrees on the bottom. Well, you start looking at that and saying, well, wait a minute, that just looks like fractions. And that's how exactly I'm going to look at it. 120 over 1, you know the zeros can be gone right away. That's like dividing by 10. So now we got 12 and 18, and I stay away from using that pi. 12 and 18, there's a factor of 6, so I get a 3 and a 2. And so when we finish this one, we're getting 2 pi all over 3 on the bottom. And notice, we do not multiply that pi out and use the decimal version, because that would even make it more messy than it already is. And so 120 degrees is really 2 pi over 3. Some people like to write it as I did here, 2/3 pi. It's the same thing. Okay, both are acceptable. Let's do, another one here. You can do any of these. How many radians is it? Every single one of these you would have to be multiplying by pi over 180. And then just do your fraction canceling. So try a couple of these, and we will share these in class to see what you have. Follow the same steps I did here. Try to do it by hand. These are all, if you'll notice, perfect combinations on our unit circle. So they are not weird combinations you have to worry about. So grab it and go. What if we have to go the other way? So we switch the fraction that we multiply by. So convert each radian to degree. So now, if I do the first one here, we need 180 degrees over pi radians. And so in this case now, the pi's will cancel immediately. You should see that 6 goes into 6 once, 6 goes into 180 30 times, because 6 went into 18 3 with that extra 0. And so now 7 times 3 is 21, add the 0. We're looking at 210 degrees. And just label your final answer, and that's how we go. So these ones, start looking at it again. You have no idea. You should have a little idea, though, based on our unit circle. But with radians, these are hard to tell. So some of them may come out to be nice. Some of them may not. I believe you're going to be fine here with all of those being fairly nice combinations. But it's in degrees that you finish with. So again, try those 3, and we'll see what you end up with for class. Now, these ones say evaluate on your calculator. Now, as soon as it says that, or it says, round to the nearest whatever, make sure you have to have your calculator set at whatever is being entered. So right there, you have to recognize that is my radians. So when you go to your mode, and this is why you're going to be toggling back and forth now, you will need to set your calculator in radians in order to do that particular problem. So now that it's in radians, and you go, hey, I need the cosine of, and in parentheses you need pi divided by 6. And so either can convert it, or you can just do it straight out. And they didn't give us a rounding answer, so let's see. I had a 0.866025, and we rounded to 3 digits. So again, sine, cosine, tangent we could use, and rounding, but you will make sure your calculator is in radians, because every single one of these is in radians. Now I want you to look at the last one here. That's not as obvious. Some people say, well, that's a cosine of 6 degrees. They're trying to get you. There absolutely has to be a little degree sign, and since there was none, you have to assume that this is still in radians, but what's the only difference? Good. Some of you are thinking that the pi has been multiplied out. So 3.14 times what gives me 6? I don't know, but gives me 6. Yeah, 3.14 times some number gives me 6, and that's already been multiplied out. So in this case, you would just do, again, cosine and put your 6 in, because that's already in radians, and ask the calculator to evaluate. I'm getting a 0.960-ish, and so rounded. So try the other ones, and don't get mistaken for something that is not in radians. All right. Now that you know about radians, and I will save it for the end, take a moment before we finish this. You have your unit circle, and it's already marked in degrees. You should now be able to go and label this in radians, and we'll show you how to do that right at the end. But if you think you know what you're doing, go ahead and try it. Remember, we said pi radians is equal to 180 degrees. All right, going back to the circle, we know that we can have the arc length as well, and we talked about radians being a measurement that we can use for arc length also. Notice what I have here, the radian measure of theta, so our unknown angle, the radian measure of a circle. So our unknown angle is to our full circle, as the arc length of theta is to the arc length of the full circle. And remember, the arc length of a full circle is nothing more than the circumference, so that's why we have the 2 pi r here. So we're doing a little ratio. The radian measure, degrees, is to its degrees, and then over here its arc length is to the full circle's arc length. So if you solve this for theta, which is the unknown, you can see we'd be multiplying both sides by 2 pi. If I multiplied by 2 pi here, the pi's would cancel. We'd have theta. On the right side, the 2 pi's would also cancel, and we'd have nothing more than s over r. So our unknown theta is equal to that s value, which is the arc length, divided by your radius. If you want to find arc length, which is what the section also says we can do, then you got to solve this for s, which means now you want s is equal to your radius times that theta value. So here's an example of how it would be used. A central angle in a circle with a radius of 24 inches measures 5 pi divided by 4 radians. So it's in radians. You're not going to have degrees. Find the length of the arc intercepted by the angle. So we want this green portion. So right away you say, find the length of the arc. Arc length is nothing more than s. So we're going to write the equation s equals radius times theta. S equals, our radius was 24. Our theta value in radians was 5 pi divided by 4. You can cancel. The 4 and the 24 go 6 times very easily. 6 times 5 is 30. 30 pi. End up with 30 pi inches arc length because it was inches back up in your original problem. So 30 pi inches, but if you multiply that out, remember pi is 3.14-ish. You have a pi key. So if you multiplied it out, we know 30 times 3 is 90-ish, so approximately a 94.2 if we use the decimal approximations. So that arc length would be about a 94.2 inches. And it would just depend on how big your radius on your circle is. That could be in feet, miles if you want to talk about a huge circle, like we were talking about land and property that way. All right? So should be good to go with that. Now I think the only other thing I'm giving you FYI, on bottom of page 853, there is some more real-life formulas that have theta as radians in it, dealing with linear speed and angular speed. There's a good picture I didn't reproduce. If you're interested, just read the bottom of that page 853. Linear speed is the measure of how fast the position of the object changes. So think of spinning something, and then whatever its force is would let go and it's going to go fly off. Linear speed. But then angular speed is the measure of how fast the angle of rotation for the object changes. So how fast is it spinning? And so we have t is time and theta is the angle measure in radians that we're traveling through. So you're going to need that to answer a few questions. But really all that's left now then is, what did you get for your radian version of our unit circle? I hope, and hopefully you can see these little pictures, but if you can't remember, start easy. And I'll go pink still here. We said 180 was pi. So if that's pi, then if you look at this as the top half of your circle, if that's 1 pi, think of it that way, if we go another half, we'd be at 2 pi. If we just look at the top half of the circle and we back up halfway, we'd be at 1/2 pi, or some people like to call it pi over 2. Then you got to be thinking, wait a minute, looking at the top half, and this would be good, because the top half wedges, notice lines, do overlap into those other quadrants. So we're going to break it up into 30s. If I break it up into 30s, which I believe, well, I don't remember, it was either red or blue, 30-degree wedges, we'd be looking at this one, here, 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 everything but the middle guy. Okay, these are all our 30-degree wedge positions, the ones that are checked. And so if you look at this, ask yourself, how many of those wedges are in the top half of this only? So I say this, fold it right here and say, okay, if we just look at that top half and we know that's 1 pi on our unit circle. how many of those marks that are checked? 1, 2, 3, 4, 5, 6. That's an easy way to remember it. And so we go around and we number those wedges. And you can see here this says pi over 6 or 1/6 pi. We go to the next one. 2/6 pi is pi over 3. 3/6, another name for 1/2. 4/6 is 2/3 pi. 5/6 pi. And 6/6 pi reduces to 1. Now we can bring the rest of the circle into play. If we're at 6/6 and we go one more sixth, then we're at 7/6 pi. 8/6 pi reduces to 4/3 pi. 9/6 pi is 3/2 pi. 10/6 pi reduces to 5/3 pi. 11/6 pi. 12/6 pi gets us back to where we started, or 0, 0, which is 2 pi. And now we've completed the whole circle. Now do the same thing, but count on your fourths only. And now your fourths, whoops, that last one was error. Your fourths are at the 90s and the middle. So our 90s and our middle. Here's our 90 and our middle. So here we go again, looking at just your 1 pi, 180 degrees. Ask yourself how many blue wedges. So if you're just looking at the wedge that creates that, you're seeing 4 wedges in that piece. So here we go, start counting. We start at 1/4, or some people would say pi over 4. 2/4 is 1/2. 3/4. 4/4, better known as 1. Then we go down to the lower half. 5/4 pi. 6/4, also known as 3/2 pi. 7/4 pi. 8/4, known as 2. And you get around the circle and you're seeing only certain denominators because of fourths, thirds, sixths that we were using. And so now you have a unit circle that cannot only be counted in degrees fairly easily, but also can be counted in radians. So knowing that and knowing where the positions lie, that's, again, another little piece to the puzzle of the unit circle. So now that you have that, we gave you arc length as well as the radians to use in this section.